So while we're waiting to start, can I just take a quick poll to scope out the audience here? First of all, how many of you are undergraduates? Okay. And how many graduate students? Okay. And how many of you would consider yourselves ringers in the sense that you probably know more about these things than is good for you? And nobody's going to confess to that few. Okay. Okay. Oh, hi. Okay, good. Just wanted to scope things out here. Amongst the undergraduates, what are your majors? Are you willing to divulge this in public here?
I'm a math and physics major.
Yeah?
I'm sociology.
Sociology, all right. And you guys know we have two physicists in theater? Cinema and cultural studies, okay. And where are my other undergraduates here? There are more, right? Well, they're not willing to say anymore. Okay. Okay, good. Thanks.
Well, with that pre-introduction, let me welcome you to the third of Jeff Weeks's talks. Yesterday we learned about symmetry in 2 dimensions in the plane, and then we learned about some symmetry in 3 dimensions and its relationship possibly to the cosmos. And today we're going to stretch our mind and visualize 4 dimensions.
Hey, thank you. Okay. Eventually here I think we can let everybody pitch in, but for the first 5 or 10 minutes, I'd like to ask that those people who previously self-identified as ringers just zip your lips for a few of the earlier questions. So thank you. What I'd like to do today is offer an introductory lesson in visualizing 4-dimensional space, and then towards the end of the hour we'll look at some applications in physics. So that's the plan. Okay, what's a hypercube? Anybody? Other than ringers here? Well, what should we make of that term? So we want it to be, it should be like a, yeah.
Equal sides, perpendicular angles?
Yeah, so we want something that's like a cube but a dimension higher. So we have a progression from, say, a line segment to a square to a cube. We want to keep going to the 4-dimensional thing. So just to get warmed up, how many corners would you expect a hypercube to have?
16.
Yeah, maybe 16. So a square would have 4, then a cube would have 8, a hypercube would have 16. How many faces? Anybody willing to take a guess?
Dimensional faces?
Top dimensional. So, yeah, maybe 8. So a square would have 4 sides, a cube would have 6 faces, a hypercube would have 8 hyperfaces, whatever we want to call them. So the point here is to sort of get warmed up to this idea of what a hypercube might be. But in a sense, we've already seen the limitations. We can reason by analogy and kind of get an idea of what we expect, but it's not very convincing. Okay, we can't really see it. Okay, so what I'd like to do today is offer you a system to learn to visualize 4-dimensional space. So instead of having to kind of grope your way along by analogy, that you could just shut your eyes, visualize this hypercube, and to count its vertices just in your mind's eye, 1, 2, 3, 4, 5, 6, 7, 8, count them out. Okay, so that's our goal for today. Now, rather than starting with our predicament as 3-dimensional people trying to understand 4 dimensions, I'd like to bump everything down a dimension and consider the predicament of 2-dimensional beings trying to understand 3 dimensions. Okay. Have any of you read Flatland? Yeah, all right. This is a wonderful book. Okay, if you haven't read it, it's written, over 100 years ago. It is exactly that. It's the story of 2-dimensional beings trying to understand 3 dimensions and then leading you to understand 4 dimensions. It's also a good dose of Victorian social satire thrown in, and throughout it makes absolutely wonderful use of the English language. If you ever have an excuse to read it out loud, don't pass it up. So, okay, let's draw ourselves some Flatlanders. Okay, here's Flatland, which I'm viewing as a horizontal plane here. Okay, we'll draw some Flatlanders. As you wish, you can think of them as stick figures, or you can think of them as polygons, as you prefer. And their immediate task that we're going to present them with is trying to visualize a cube. Okay, that's supposed to be a cube intersecting the plane of Flatland. And clearly this isn't so easy for them because the cube doesn't fit into their space. However, their ability to visualize 2-dimensional objects is excellent. Okay? So what I would propose for them is for each point, say x, y, z here, for each point we'll ask them to keep track of the x and y coordinates just using their built-in 2-dimensional intuition that they're comfortable with, and then keep track of the third coordinate using color. Okay, so what we'll do here is for color, for the bottom of this cube that lies down below the plane of Flatland, we'll color that red. Okay, so in terms of coordinates, that would be, say, z equals -1. Okay. Up at the top face of this cube, we'll color that violet. So there's z equals +1. Halfway along, where the cube intersects Flatland, we'll color that green. So that's z equals 0. And in fact, you can think of this whole plane of Flatland as being green if you want. And so on. So imagine all the intermediate colors filling in here. So there's an orange level, a yellow level, a blue level, and not just those, but a whole continuum of levels going through there. Okay, so that's the system. Each point's represented by its x and y coordinates that they can visualize, plus color for this mysterious third dimension. Of course, we're kind of cheating here because we're drawing this as we see it, and the Flatlanders can't immediately see that extra dimension. So their picture would look more like this. Okay, different versions of Flatlanders here. In their version, okay, they'd see the base of the square, the base of the cube, like this. Where are they going to see the top of the cube? Same place. Okay, same place, but just a different color because it's at a different height. Okay, and so on and so forth. So here's the middle section and all the other colors as well, all stacked into the same place. Okay, in this picture, can you show the Flatlanders where the cube's 8 corners are? Or explain it, or say. So I guess to specify a point, if these 2 coordinates are going just by intuition, this one is color. So if I want to specify a point, I can go red, and I've called out a point. Okay? And go blue. Now I want to say violet. Ignore blue would be here. I want to do a corner. Red, violet. Okay, so we want to specify all the points. Red, violet, red, violet, red, violet, red, violet. There are the 8 corners. Where are the cube's edges in that picture? Can you show them to the Flatlanders? Yeah.
Well, in the same way that you've dealt with the vertices, you can deal with the edges between them, but that's only some of the edges. Then there are like vertical edges that don't make sense in Flatland.
Okay.
Well,
Want to come up and point those things out, please? Oh, and by the way, the chalk will make a mess of your hands if you use it, but there's some wet paper towels here if you want to go back to your seat with clean. Oh, okay.
So, like, we dealt with, there are 2 vertices there, 2 vertices there, and 2 vertices there, and 2 vertices there. For each of those pairs of vertices, there's an edge there. So it's like there are 2 edges there.
Oh, okay. So say there's an edge,
there.
Red
Right. There's like
and
a
violet,
edge.
red and violet, red and violet, red and violet. Great. So we're up to 8 edges.
We're missing 4 of them.
Yeah, we're missing 4. What happened to them?
And I have no idea how to deal with that.
Ah, okay. Thank you for your contribution, having found 2/3. Okay.
You can just have a point and vary the color, varying the spectrum at a single point from
Aha.
violet.
Okay, we could have kind of a rainbow edge here. So we just go here and go red, orange, yellow, green, blue, violet, while leaving our finger sitting still at one point. So it would be kind of corresponding to a vertical edge going red, orange, yellow, green, blue, violet. So here's this rainbow edge here, rainbow edge here, rainbow edge here, rainbow edge there. So there's the other third of the edges. Great. How about the faces of this cube? Can we show those to the Flatlanders?
Two of them are obvious.
Okay, so
Colored red and violet.
Yes.
okay, so we have red and violet. So there are 2. And what about
It'd be a rainbow for each vertice that the Flatlanders can see.
almost. So for each vertex, for each edge here, we run that through all the colors. So we have red, orange, yellow, green, blue, violet. So we have that edge sweeping out a face. So that'd be a vertical face up here. Great. So we have the one red face, the one purple face, and then 4 of these rainbow faces. 1 + 1 + 4 is 6. So we've got all the faces. Good. Was there a question? Yeah.
I mean, why isn't it easier to use Abbott's original thing and use time as your extra dimension and have the things thinking through?
We could use time. There are reasons not to. One is that when we eventually want to use time to represent time, then we'll still have time left for that purpose. And
Monkeys
I think,
visualize the thing moving through the plane.
and I think
What do you see?
it's easier, but ultimately less productive or less powerful. I think the goal is to be able to visualize 4-dimensional space the same way you'd visualize 3-dimensional space. Just kind of shut your eyes and see it and get the picture. And I think there, using time is expedient in the short run, but it slows you down in the long run towards the goal of actually visualizing it.
I have a tiny complaint, though.
Okay.
I sort of feel like you're looking at the same. Let's say we're talking about edges.
Yeah.
So we're dealing with an edge of a cube, which is a uniform thing. It should be the same everywhere.
Yeah.
But in this 2-dimensional space, some of those edges exist in points, and some of them are like line segments.
Yes. Okay, a good objection. So the objection is, in the technical term for this is we've broken the symmetry. So this cube has this nice symmetry, and we've made an arbitrary choice, namely of its 3 dimensions. So it has x, y, and z. We arbitrarily decided that we are going to kind of flatten along z. We could have flattened along x, we could have flattened along y, and I'm really happy that this bothers you, because this sort of thing bothers me too. In fact, my advisor in graduate school, who gave me much good advice, I think most of which I never even understood, even at the time. But one thing I did understand is that he said, in mathematics, you should never make arbitrary choices. Only do things that you're forced to do. And if you find yourself making an arbitrary choice, go back and rethink things and find a way to proceed that doesn't involve arbitrary choices. So yes, this is a flaw in this picture, and I think the ultimate resolution is that the Flatlanders need to think long and hard about this And when they get really good at it, then they should try to, maybe learn how to rotate that cube or sort of get themselves past this idea of having one preferred direction. So yeah, so I will plead guilty that this is a temporary crutch. Yeah.
Are the squares kind of only partially shaded so you can actually really see two colors at once?
Ah, this is an excellent question. Okay, I'm glad you mentioned that. Each square is absolutely filled in with no gaps, and that's true for all of them, for all colors. So it's not a physically realistic thing that each one is completely filling that area, and they're superimposed, they're occupying the same area.
How do you see a rainbow, or how do you see 5 colors at once?
In your mind. Okay. Eventually, we're gonna straighten them out. Because see, this is just the initial picture, and I think within about 10 or 15 minutes, this will be clearer. But the idea is that the Flatlanders are going to learn. They'll start with the colors, and then they'll separate them out and have a mental image in which they're spaced out in the third direction, in the third dimension.
Because I think if I were to this issue with time, if I were to imagine 5 colors at once, I might think, red, then orange, then yellow, then green.
No, these are absolutely superimposed, and not only 5. Imagine reddish orange and orangish yellow and the whole spectrum of colors filled in between. Okay, so there's a lot of stuff superimposed here, and in fact, that's really the challenge here. It's in your mind to separate it out, and that's what you need the extra dimension for. Okay. Okay, so we've got this nice picture here, well, a good enough picture for the Flatlanders to understand this cube at some level. Could I have a volunteer, please, to draw the analogous picture of a hypercube? So here we have a 3-dimensional cube drawn in 2 dimensions. Could somebody make a picture of a 4-dimensional cube drawn in 3 dimensions with the aid of colors? Yeah.
It is unfair because we have only 2 dimensions to draw. So.
Right. Yeah. So there's an extra challenge that there are 2 levels here. That there's going to be on a 2-dimensional blackboard. There'll be a picture which all of you, by virtue of your extensive experience in seeing 3D, will visualize as a 3-dimensional thing, and then that in turn will represent a 4-dimensional thing.
It's a projection of projections.
Yes. And you're welcome to these colors if you wish.
Okay. So now, I guess I'll start at the bottom. So really think about drawing this whole thing out in red first and coloring everything inside. And I'll draw the top. There. Follow your pattern. I'll draw halfway in between now. Thank you. Any more colors?
Good.
Infinite. I'll start using the green and the yellow at the same time.
Okay. Thank you very much. Okay, so here we have a color-coded picture of a hypercube. Where are its corners? And indeed, how many of them are there? Can we have a volunteer to come down and just start, well, red and violet and Seeing how many corners we can fish out of this?
It's up to 16.
Okay.
It's clear. It's the 8 red ones and the 8 violet.
Okay, 8 red ones and 8 violet ones. So red, violet, red, violet, red, violet, red, violet, red, violet, red, violet. Okay. How about the faces now? Whatever the analog of the sides of this thing. How many are there and where are they?
Well,
Should have come through ages.
So for each edge, you can say, okay, that edge is of each boundary color, and then for each vertex, for each apparent vertex, you have an edge.
Okay, so I think there are different things being computed in different parts of the room here. Okay, so I guess here we need to distinguish what kind of pieces this thing has. So we counted kind of the 0-dimensional pieces, the points, and we got 8 of those. Then we counted the 1-dimensional edges of this thing, and we got how many of those? 12 of those. And then we counted the 2-dimensional sides, and we got 6 of those. And that's as high as we got here, because then we've got the whole thing. So here, okay, so we counted the 16 0-dimensional things. And now there's some question, what do we want to count next? Where should we start?
1 dimension.
Third one of the obvious things.
1, okay. Okay, how many 1-dimensional things are there in here? Well, let's see. Well, can somebody say or show where they are? 32? One? Yeah.
Oh, you want edges? Like this is the
Yeah, we want, I think now we're counting 1-dimensional things.
Okay. So there's red, violet, red, violet, red, violet, red, violet, and so on for each of the. So for each of the 12 edges, which you see in a normal cube, there's 2, so that's 24. And then there's also a spectrum, 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 spectrum. So that's another 8. So that's 32.
Okay, great. So what about the 2-dimensional things in there? Thank you. 2-dimensional edges or faces, whatever you want to call them. How many of those are there? Okay. Yeah, so what do we have? So we have, so here's when he's saying 2 times 6 plus 12. Okay, yeah, so we have what looks like the 6 apparent faces of a cube. So red, 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 violet, 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 violet. So we've got, so we're up to 12 there. Okay, and then each of these 12 edges goes through the spectrum. So we've got another 12, so there's 24. And how about the 3-dimensional sides of this thing, the 3-dimensional faces?
Plus 1 plus 6.
Yeah. Yeah, 1 plus 1 plus 6. Yeah, so we have a whole red thing, a whole purple thing, and then the spectrum ones for each face. So we end up with 8. Great. Okay, when you talk about these things, there's a gap in the English language in that we have words for left and right, backwards and forwards, down and up, but there isn't any really common word for moving in positive and negative directions in the 4th dimension. And in the late 19th century, though, this guy Hinton coined some words for this. He took the roots from Greek for upwards and downwards, and the words are kata, means moving in the negative direction, and ana is the positive direction in the 4th dimension. So the red face here is the most kata word, and the violet one is the most ana word. So they're good. They save you from embarrassing moments about, well, is it up this way or is it up in the color direction? So Anand do that. OK. I'd like to now return to some objections people made earlier about, well, breaking the symmetry there by picking one preferred direction. And, could they really see infinitely many things all crammed in the same place? And this is where we need to make clear the philosophy behind this undertaking. The color coding is like, it's a first step towards visualizing four-dimensional space directly. But it's a useful trick. Okay, it's clearly not real visualization. But the whole purpose of this is like a temporary crutch that the color coding gives you a way to start getting some experience with four-dimensional objects. And as you start getting some experience with four-dimensional objects, you start to get a glimpse of what four-dimensional space really looks like. And once you start to get a glimpse of that, then it becomes easier to get more experience with a wider variety of four-dimensional objects. And that extra experience makes it even easier still to visualize 4D. So you get a virtuous cycle going here. And once you get that cycle going, whoops, you don't need the color coding anymore. Okay, so at that point, you just forget the color coding. And when you imagine these pictures in your mind, you just kind of sense what's more kata-word and what's more ana-word. Okay, what do I mean by, well, you just kind of sense this? What I mean is you try the following experiment. Okay, in the 3D room, okay, you cover one eye, so you don't have any depth perception to speak of. You don't have much anyhow. Okay, and you look around. The image on your retina is a two-dimensional image. Okay, so for example, I'm looking right here on my retina. I see John, and right next to John's face, I see George's face, and right next to his face, I see the face of the guy from cinema and what was it?
Cultural studies.
Cultural studies, thanks, yeah. So all three of you guys, your faces are right next to each other on my retina, but I just kind of know that John's closest, then George, then, I should have asked your name, but then Pete, okay. Okay, I just kind of sense where these guys are in the room, okay? And that's the same impression you'll have working with these pictures, okay? You just kind of sense that red face is more kata-word, the violet face is more ana-word, and you sense it even when you stop drawing the colors in there. Okay, let's try a few exercises with this. We'll start with some easier ones and work our way up. Okay, using a fourth dimension. Okay, so say, for sake of discussion here, in this four-dimensional space, we're all in the green slice, which is convenient with these chairs here. So it looks pretty green. Okay, so we're in the green slice here. How can I get out into the hallway without opening the door? By using a fourth dimension. In the language of colors, what has to happen?
Shift yourself in color.
Yeah, shift myself in color. So say I turn blue. Okay, so I move ana-ward in the fourth dimension. I walk over the door, not that kind of over, but ana over the door. And then I shift redward again till I'm green again on the far side. And then I'm in the hallway without having opened the door. Yeah, it would. Okay.
In that case, it's easier because you're using time.
No?
Yes, because you're taking the seat. I mean, since you're walking the door, it's not, you see yourself changing color as a progression.
Right.
You go through, you see yourself again changing.
Yeah.
Progressions.
Yeah.
It's natural to use the time.
Okay.
Separate things.
Although in that sense, time is distinct, though. Time is one variable, and my fourth coordinate is a different variable here.
Yeah.
And so my time is marching steadily forward here, but my fourth coordinate is going to increase and then decrease. So in the second half of the trip, the coordinate's decreasing, but time is still increasing.
If you were to use time, you could go back to before the building was built.
Oh, there we go. And just
Come back.
Watch it being built.
Yeah. just so the floor was in place before the door.
That's your problem.
Okay. Okay. So an exercise for you here. Here's a tetrahedron. So there are two parts to this exercise. The first part is to make some sort of color-coded picture to explain the tetrahedron to the Flatlanders. And then the second part will be to make a hypertetrahedron and count its vertices and its faces. So part one is, would anybody be willing to draw a color-coded version of the tetrahedron for the Flatlanders? Okay, great. Thank you.
So the faces are all equilateral triangles. So I think I would have a green. Well, actually, it depends.
Depends where you put it.
Yeah, it depends where you put it. If I'm putting it in the middle, ideally, then we have a little green equilateral triangle. And as you go down, it's going to sort of turn red and get bigger. So I'm thinking that there's going to be kind of something like that, and the colors in between would be there. So let me come up with something like orange. And I think we're maybe yellow. Yellow comes after orange. And I would sort of continue this progression inside. Blue. Oh wait, that's I wanted. Oh no, that's fine. And then the violet would be at the very center. Sort of like that.
Okay. Thank you. What do you think? Good? Okay. So how about a hypertetrahedron? That's what this guy always says. Obviously the same thing.
Red shrinking to.
Well, let's. Okay. Let's see. Would anybody like to sketch it? Would you like to sketch? You got to watch out for things that are obvious. I
think my drawing abilities are limited, but.
I don't think I could draw a tetrahedron.
So, I have to. The surface of it, only the surface of it is red, right? And then you have. I'll just do 3 tetrahedron.
Are we talking about?
Yes, you're right. The whole thing is red.
Are we talking about a film?
Yes, you're
Are we
right.
talking about like a
The
song?
whole thing is red.
Yeah, so it wasn't
And
obvious.
inside it, yes, the whole thing is red, and then there's an. And it's green. Inside it, one point.
Okay. Thank you. So, how many vertices? How many corners does that thing have? 5? Yeah, so it's got in red, so it's got red, 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 red. There are 4 of them, and violet is a 5th. Okay, good. For if we take in 3-dimensional space, let me think. Actually, let me think how I want to proceed here. Yeah, if in 3-dimensional space, so this axis is, they're all supposed to be perpendicular, these 3 axes. If we go along and mark out points plus or minus 1 units out on each axis, and then connect them all, okay, we get what's called a convex hull of these points. Okay, it's kind of a crummy drawing. It's supposed to be an octahedron here. So how would we make a drawing for the hyperoctahedron? Anybody?
So red and violet would coexist in the center.
Okay.
Then we'd radiate out to green on the outside.
Okay. Would you like to draw?
This is provided that we're facing one of the points like this structure. So the whole thing, all of this tetrahedron glory is green, and then internally we have both points, tiny violet octahedron and tiny red octahedron coexisting. And then in between we have orange and things like that.
Okay, great. Thank you. How many vertices? Yeah? Okay.
7.
What'll it be? Well, where are these vertices? What location and what color? Yeah?
Each of the axes arcs and the one in center.
Okay, so we have green, 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 green. So we have the 6 vertices of the octahedron in green. Okay, and
In the center.
yeah, then we have red, violet. Okay. Okay, so kind of like for the original octahedron with the Flatlanders, we could draw it. Whoops. We could draw it like this: red and violet, and then they connect up with appropriate rainbow arcs. We'd have 4 plus 1 plus 1. Okay. Oh, the faces here. How many three-dimensional faces does this thing have? Can you see them in there? Yeah, let's think. Where are they? Yeah. Here, I'll draw it. I'll draw just the skeleton of it so we can see the inside a little more easily. Okay, so we have that. And red, violet, and then these things connect up accordingly. Where are they? Where's even one of them? I think if we find one, then it'll be.
What are we looking for?
Okay, we're looking for three-dimensional faces.
Yeah, you have to take a triangle and how it sweeps out both ways. So one way is one face and one way is the other face.
Yeah.
There were 8 two-dimensional faces on the three-dimensional one, so it sweeps out in 2 directions. And that's 16.
Okay, so we can take of each of the 8 two-dimensional faces. I just colored one to not clutter up the drawing. So we can take that, and the suggestion was that that sweeps along that green face together with the red vertex, makes a three-dimensional tetrahedral face that tilts contoward. The same green face tilts onward towards the purple one, so therefore there are 2 three-dimensional faces for each of these two-dimensional ones, therefore 16. Okay, very good. Okay, in a moment here we'll go on to the physics, but first I'd like to propose a couple more advanced questions that mostly with the ringers in mind here, just so nobody goes away feeling under-challenged, but you're all welcome to, encouraged even, to think about them. Okay, one of these questions is the following. This is the lower dimensional version. If you take a cube and you take alternate vertices, so every other one, so this, 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 you connect them up, okay, and you get this convex hull of these points is a tetrahedron. Okay? How about one dimension higher? If you take a hypercube, take alternate vertices, connect them up to get their convex hull, the question is, what is it? So again, no computation required, just the shut your eyes and visualize exercise. Okay? That's one of the advanced exercises. The other exercise, I'll tell you the three-dimensional version, but with the warning that the three-dimensional version is harder than you might think. But once you're happy with that, then the four-dimensional version is easier than you might think. The three-dimensional version is the following. Take a cube. Does everybody have a cube in your mind's eye? Take two diametrically opposite vertices. Okay, take your cube, rotate it around. There are those two diametrically opposite vertices. Take a slice halfway through. What's the cross-section of that cube?
A hexagon? Or?
Yeah, it's a hexagon. Okay, but it's not obvious. At least for me, I start to really strain a minute to see that hexagon. It is indeed a hexagon. Okay, that's the exercise that's harder than you might think. Then the next part is, well, what's the four-dimensional analog? If you take a hypercube, take diametrically opposite vertices, slice halfway through, what's that slice? And just to point out why things are at least technically simpler in 4 dimensions, we'll come back to the problem of the ordinary cube, which I have a terrible time drawing this, so forgive me if it doesn't come out looking very good. This is supposed to be just an ordinary cube, but drawn with...
It's a dodecahedron. Is it a 12 thing? Sorry.
Okay. Okay, that work out okay? Yeah. Except I should have drawn that dotted maybe. Okay. Okay, this is a cube drawn with one vertex high and one vertex low. You think, well, how would we present this to the Flatlanders? Well, here's this bottom vertex, the cottommost vertex. We draw it, and now these 3 edges coming upward from it, excuse me, not cottomward, just lowest. Here are the 3 edges coming up from it. They'd hit maybe yellow vertices. Then there are 3 more edges coming up from those. So these things are all parallel. They're just 3 directions you need to be working with, and that's it. Whoops. Make sure I'm using, yeah. Okay, so that gets us up to the blue vertices. And then finally, we come back to the center, and that gets us to the purple vertices. So this is a view, for the sake of the Flatlanders, of a cube as sitting kind of vertex on. Instead of sitting on a face, it's sitting on a vertex. So this is how they'd see it. Now, what makes this nice is when you draw kind of triangular type things in the plane, they don't sit very well with the common xy coordinates, because you're used to thinking of things kind of rectangular. You don't have to, but our experience is we think of things in a rectangular kind of way, and this just isn't a rectangular kind of picture. But when you move to the 4-dimensional question, you think, well, this must be worse, because now rather than having this sort of triangular thing where we're going to have a tetrahedron sitting in there somehow. But the nice thing with a tetrahedron is that a tetrahedron sits very nicely. Can't talk and draw at the same time. A tetrahedron sits very nicely inside a cube. So here's a cube which is drawn purely, this is like the grid lines on the graph paper. It's not part of the final drawing. Then we're going to play this game of taking alternate vertices. I shouldn't have drawn in yellow, though, in green. Well, that's okay. Pay no attention to that color. Okay, so they're the vertices of a tetrahedron. So when you start drawing the analogous picture for your hypercube, radiating out from the center, corresponding to these vectors, okay, here's the center, so that would be the cotawardmost point. And then we're going to draw, instead of having 3 arrows coming out, we're going to have 4 arrows coming out. And you can send them out to the alternate corners of this cube. So everything's going to line up pretty nicely. And then you can just continue playing this game to construct your hypercube as seen from a vertex rather than as seen from a face. And then you can ask yourself, well, what's the halfway thing? Just like you could ask, what's the halfway thing here? But believe me, in this case, it's even easier to find the halfway thing than it was here. OK. What do we have? About 10 minutes. Let's pass on to do some physics. OK. OK. OK, so up until this point, we've been talking about 4 dimensions as 4 spatial dimensions. Now we're going to use the 4th dimension to represent time. Okay? And ultimately here, we're going to be talking about a 4-dimensional space-time for our own 3-dimensional world. But just to get started, we'll draw the pictures 1 dimension lower. We'll draw a 3-dimensional space-time for a 2-dimensional world. Okay? How many people have seen space-time before? OK, well, have seen the theoretical construction. We've all seen it. OK, how many people have not? OK, about even. Let me draw a quick picture here. OK, so yeah, how many people have seen space-time? Right. OK, in brief, here's space. So this is a 2-dimensional space for the moment now. And we're thinking astronomically. So here's the sun, the Flatlanders' sun. Okay, here's their planet, a flatland Earth. And this picture is drawn on the 4th of May. Okay? If we go forward in time, so say we go up to June here. Okay? The sun is still here. What's different about the picture, though? Earth is in a different place. Earth has moved, whatever, 1/12 of the way around. So we go up to the next level. Sun's still here. Earth has moved a little bit further. Okay, we'll go through, we'll fill in all the intermediate levels. So the sun, which is a disk in Flatland, once you fill in all these levels at all possible times, it becomes a solid cylinder. Okay, and the same for the Earth. It's a disk, but then it sweeps out a cylinder, which follows a helix going through here. So that's a Flatlander solar system as seen for a few months of space-time. Okay, and what I would like to do here is make 2 copies of this picture, because we're going to contrast 2 points of view here. So excuse me one moment while I draw the pictures. Okay, here's the sun in this picture. Here's the Earth coming around. Okay, exact same picture for the moment here. Here's the sun. And here's the Earth coming around. Okay, physically these 2 are going to be the same, but I want to give them different interpretations. Okay, this picture we'll call the moving now. Okay, what do I mean by the moving now? In the moving now picture, we come in here and we find the 4th of May. Here's the slice that's the 4th of May. Okay, this is the slice that's real and alive, so we're going to draw it as glowing. Okay, so that's reality, that's today, that's now. Okay, of course, as time passes, now sweeps upward through space-time. So it's kind of like a movie running through a projector. You're watching now go on up through. Great. That's the moving now picture. Okay. The other picture we'll call, well, tentatively, let's call it the no now picture. In this picture, there is no preferred slice. We just look at space-time. Everything's there. Nothing's glowing. But I think a better way to look at this is not that nothing is glowing, but that everything is glowing. So kind of all the possible slices are all real and alive and animated. So really we want to think of this as the all now picture. Okay. In a moment here, I'd like to offer some reasons why you might actually, well, first of all, which corresponds to the way we normally see the world?
The moving now.
Yeah, the moving now. Okay, the reality time, we just pass up through this thing. The slice moves forward. I'd like to offer some reasons why you might actually prefer this picture. Okay, but before saying why it's better in some sense, I want to make clear just what it is that it's saying. And so for that purpose, having thoroughly cleaned my hands here, could I borrow your book for a moment, please? Okay, here is the biography of this young man's life. Okay, it's all right here from his birth on page 1 to his death on page 492. Yeah. Okay, and now we want to say, well, how does the character in this biography perceive things? What seems real? So we go here on page 142. Is it here? Okay, here you are. You're at Stony Brook University in a seminar, and on this page we say, well, what seems real? Well, this page seems real. Earlier pages, for example, playing in the mud as a 2-year-old, okay, that does not seem real because that's in the past. Okay, and we say, well, what seems real in the future? Okay, says, yeah, only page 51 seems real. If we go in the future, for example, where his first grandchild is being born on page 258, that seems pretty unreal, okay? Now, on the other hand, okay, what page? 142, that's the page for right now? Okay, when we ask on page 142 what seems real, he's swearing up and down. 142 is the only real page. On the other hand, if we shift forward here to, yeah, okay, there you are. You've just got, a nice job, whatever. Things are going pretty well up on page 213. But we say on 213, what about that page 142 that was so great? No. Page 142, that's in the past. That's done and gone. That's not real. Okay, events in the future, like retiring, okay, that's not real. That's in the future. Okay, so from any given page, when we ask him what seems real, only that page seems real. Everything else is done and gone or yet in the future. Fortunately, okay, we don't have to confine ourselves to these narrow points of view. We can stand back, look at the book as a whole, and see all the pages as equally real. Thank you. Okay? And it's the same deal with space-time. Normally, we perceive space-time one slice at a time. Okay? This slice, May 4th, seems real. April's done and gone, not real. June hasn't happened yet, not real. So the goal here is to step back from space-time, see all events as equally real. Okay? All equally alive, all equally valid in some sense. Now, of course, the ultimate goal is not to see it on a blackboard this way, but to visualize it in reality this way. So if you could, try the following exercise. Okay, here we are right now at 255. And so here we're at 255. This is the green slice of our space-time. Okay, imagine when you are first coming into the room to take a seat for the lecture. You got that picture in your mind? Imagine that as the red slice, kata word. Okay? Imagine 5 minutes from now we're getting up to leave. Imagine that as a violet slice. That's ana word. Now imagine all these things superimposed in this room, but just in different colors, red or green or violet, more kata word, more ana word. Imagine them all at the same time. So that's space-time. Okay? And I think as long as I'll take questions in a moment, but let me just say briefly why the reasons are that you want to prefer this over this. There are two reasons. One of them is there's a deep conceptual flaw here, and the conceptual flaw is that there are two kinds of time in this picture. There's the coordinate time marked by how high up you are, April, May, June, but there's also watch time relative to which this slice is moving upward. So we have two kinds of time. You really want two kinds of time in your picture. If you try to merge them, that doesn't help, because then you're saying, well, in April this slice glows, in May this slice glows, in June this slice glows. You end up with all the slices glowing, and you're back to this picture. Okay? That's one reason. Okay? If you want something a little more hard-nosed for why you should prefer this one, it's that special relativity tells you that different observers it's called the theory of relativity, but it could be called the theory of absolutism, because special relativity gives you an absolute space-time that everybody agrees on. What's relative is that different observers slice it up differently. So an observer at rest relative to the sun sees these events as being simultaneous. Another observer speeding by in a rocket ship sees a different slices space-time differently, sees these events as being simultaneous. So depending on your state of motion, you disagree about which way the slices are, even though everybody agrees about what space-time is. Okay, so I think that's a good place to stop. Thank you. Yeah, it is. I will confess, it is now 2:58, so if anybody has to go, feel free to sneak out, or if you have questions, we can answer them.
How long did it take you to internalize the no time picture?
To internalize, to paraphrase Bill Clinton, it depends what you mean by internalize. I think, reading about it, say, over the course of, a few weeks reading about this, digesting it, I kind of got it and could see it, could look back and say, okay, Caesar crossing the Rubicon, that's every bit as real as the bunch of us sitting here speaking. As far as just living everyday life, I think I'm still stuck back in the moving now. Any other questions? Yeah.
I noticed earlier, and I'm more of a math person myself, so to me, I like the idea of not considering time a spatial dimension. Mm-hmm. I like thinking about those two things as separate things. Yeah. And, in mathematics, we can deal with as many number of dimensions as we like and parameterize everything and have fun with that. But I noticed that as soon as you started talking about physics, you deal with time as though it is a spatial dimension. It seems that way to me, at least.
Yes. And I think this is intentional and a good idea. And the reason is because, two reasons. One is we want to visualize things. So our imagination works spatially. And so if we want to see different things at different times all in one picture, it's going to be visual, it's going to be spatial. Mm-hmm. And the other reason is that special relativity forces us to put space and time into the same picture, just because different observers are slicing things differently. So we cannot separate space from time, because then we'd have big arguments about how we were going to slice it up.
That would be inconsistent with observations, basically.
Yes.
Okay. Right.
Yeah. So special relativity forces you to weave space and time together. I should mention a crucial thing here. If everybody's seen the book Space-Time Physics by Wheeler and Taylor, I think. They do nice parables. They explain this beautifully. There's the question of units. Okay, and the analogy they make in very quick terms, it's almost as like you're measuring miles in one direction and kilometers in another direction. And if you try to do things like the Pythagorean Theorem with miles going one way and kilometers going the other way, it's not going to work out well. You need to get some sort of conversion factor for how many kilometers per mile, convert them to the same units, then you can do the Pythagorean theorem, you can measure distances, all that. We're in a similar situation here, that by historical accident, essentially, I mean, obviously steeper than that, but essentially by accident, we measure space-like distances in meters, we measure time-like distances in seconds, and we spoil an otherwise beautiful Pythagorean theorem. There is a unit conversion between meters and seconds. And the simplest way to say it, it's 1 light year per year. Okay, so the speed of light, and let's see, I always have to think whether it's 10 to the 8th or 10 to the 10th. Let's see, so it must be
10 to the 8th.
Yeah, but then I have to decide what I'm going to say over here. So it'll be 10 to the 8 kilometers per second. Meters per second. All right. Okay, so 3 times 10 to the 8 meters per second. This is just a unit conversion factor to overcome this sort of historical accident that we're using different units for space and time. So once you convert to the same units, then you can do the Pythagorean theorem. You can measure using exactly this, measure, instead of calling it distance, it's called an interval. But what it tells you is things that are roughly horizontal, that tells you the proper distance, meaning the distance between two events as measured by somebody for whom the events are simultaneous. And the same interval for things that are more or less vertical measures the proper time as experienced by somebody traveling along that path. So somebody for whom those two events take place in the same place. So there's deep physical meaning, but it only works once you convert to consistent units. Yeah. Yeah.
For certain like particles in light that travel closer to the speed of light in three-dimensional space, wouldn't they be traveling through the fourth dimension at a quicker rate, and it would kind of not be flat?
No. So once we convert to units of light years and years, then the speed of light here is a dimensionless 1. So light travels along 45-degree lines. Okay, things traveling close to the speed of light are not quite at 45 degrees, but they're still, well, the key thing with this Pythagorean theorem, there's a minus sign on the time-light coordinate. Okay, so if you have if x and t are very close, okay, you have x squared minus t squared rather than plus t squared. So this is going to be some very small amount if those are almost equal. So it's telling you this is like the twin in the rocket ship who flies out and experiences very little time relative to what the twin who's staying home here experiences. But the whole story, you don't need extra dimensions or anything. The whole story is just playing out in space-time here with distances measured in consistent units and with the minus sign. But there's no more, I had temporarily hidden those facts, but I'm not hiding anything else. That's the full story. Okay. Yeah.
So these tricks are very useful for sort of going one dimension beyond what you're used to. But do you know any tricks for going multiple dimensions? In particular, it'd be very useful for me to be able to visualize a 14-dimensional tetrahedron. There is legitimately a specific reason why it's useful.
Yeah. No, I'm for visualizing it. Personally, I stop at 4. That at 5 dimensions, kind of, by analogy, you can sort of, kind of understand what's happening. But as far as just, shut your eyes and try to do 5 dimensions, no, that doesn't work for me.
Brightness for 2 more
Yeah.
dimensions.
Yeah, you could, but that would get you. Remember, the color coding is just a crutch to get you started into building up some intuition. So you could use saturation and brightness to get a better crutch. But then there's the question of, can you eventually transcend that and actually see 5 or more dimensions? For me, the answer is no. I'm not sure. Maybe somebody has had better luck.
Add smell.
Yeah, you could add smell, but again, there's the question that came about sort of unifying things into the same picture. And I think the nice part about the 4D visualization is it's using the same part of your brain. It's giving you the same subjective sort of experience as visualizing 2 dimensions or 3 dimensions. It's seeing the picture. And with the warning, as we were talking about at lunch the other day, that you have to be careful where you do this. And I found that, like I go out for a bike ride each afternoon. It's nice. And if I'm thinking about some sort of math issue or something, if it's a logical question, I can safely ride the bicycle and think about something. But if it's visualization, as soon as my brain is, seeing tetrahedron, hypercubes, and things, then I'm not seeing the road, or let alone small children.
Close your eyes while you're.
Yeah. Yeah.
It relates to what I was going to ask you, which was, do you ever, in your everyday experience, just get flashes of seeing things in the 4th dimension? And also, this might be a personal question, but do you ever have dreams that are sort of in the 4th dimension?
Yeah, let me think. So, for flashes, I think it's one of those things I've probably been thinking about far too long now. So there's something where there's some 4-dimensional relevance, and I think I would just kind of see it as without having to strain. For dreams, I think the answer is yes, and I'm not any time recently, so I can't. Although, on the other hand, with this example about, where did it go? Drawing the picture of generalizing this to draw things going out that way. That actually, I wasn't going to talk about this way today. When I woke up this morning, there's that precious moment of thought when you first wake up and you haven't gotten out of bed and your mind's sort of a little freer than it normally is, that thought sort of showed up without my having gone looking for it. So maybe that would count as a positive answer to your question. Okay, shall we adjourn? Thank you all for coming.